My name is Nori Jacoby. I am a research group leader at the Max Planck for Empirical Aesthetics in Frankfurt. Today I want to present REPP, a technology to run online tapping experiments. We named this technology after Bruno Repp, who hosted this workshop for many years in New Haven and has been enormous inspiration for timing researchers, including myself. This work was developed in my computational auditory perception group, together with my postdocs Manuel Angalada-Tort and Peter Harrison. The motivation of this work is to develop a practical tool for collecting online tapping experiments. This is especially important in the context of ongoing pandemic, which limits the ability to collect data in the physical lab. However, tapping experiments requires precise timing, which is very hard to obtain using standard web technologies. For example, measuring the spacebar in a web browser would be simply not sufficiently accurate. For this purpose, we developed a new technology that uses audio and signal processing. Participants simply tap on the surface of a laptop and record them as well as the stimulus that is played in the laptop speakers. The trick is that after the recording, we apply a signal processing pipeline to completely separate the recording audio into three components: the tapping, typically in the low frequencies, the stimulus, typically in high frequencies, and the markers played at the beginning and the end of the stimulus in order to align this component, which results in precise timing. Manuel Angalada-Tort, the first author of this paper, will show you a demonstration of our technology in action.
This is an example of an isochronous tapping task. Participants' goal is to tap in time to a regular metronome sound. Importantly, we inform participants that at the beginning and end of each rhythm, they will hear 3 consecutive beeps. They cannot tap during these beeps as they are the marker sounds used by our technology to precisely align the stimulus with the tapping response. Let's start tapping. At this point, the recording is uploaded to the server, where we analyze it on the fly with our technology. In this other example, participants perform a beat synchronization task to music. We add a metronome at the beginning of the music to help them find the beat. Let's start tapping. After each tapping trial, our technology analyzes the participant performance online and outputs relevant metrics. For example, on the top left plot, we can see the raw recording and whether the quality was good or not. In the top middle plot, we can see the overall mean and standard deviation of asynchrony. And on the top right plot, we can see participants' asynchronies when the metronome was played and when it wasn't played.
In our preprint, we report on the accuracy of our system. We compare tapping responses simultaneously measured with our technology and with a separate calibration hardware, and found that the measurement error was less than 2 millisecond average. We then showed that when participants perform simple isochronous tapping with our system and then again with a lab-based system, the performance, mean and standard deviation of asynchrony, has the same reliability in the lab and online, that the online and lab technologies produce correlated results across individuals. We then showed that the reliability is preserved when we turn to a large cohort of online participants from MTurk. Here we replicate results originally found by Repp and Keller, namely that musical training correlates with tapping standard deviation. Finally, we could replicate also a very complicated tapping paradigm, one suggested by an earlier work by myself and Josh McDermott, and the results beautifully match to the results of the lab from a large cohort of online MTurkers. There's a preprint available online, and there's going to be code available soon. If you're interested in working on this kind of massive online experiments, you're welcome to contact me directly.